All right, so welcome to another lovely Monday, first Monday of November here in Math 202. Before we dive into where we're going, what we're going to do today is I'm going to introduce you to a new kind of integral, by the way. Now that we've started, I've introduced to you these things called fields, we'll start looking at some other kinds of integrals. That's our goal. But before we do that, as always, I will turn it to any homework questions, anything we want to chat about stuff we've talked about so far.
Is the vector fields homework still due tonight?
It is, yes, vector field. So that's 6.1, I believe,
Yeah.
is due tonight. 6.2, I did extend that to next week.
Okay.
And I just did that like, a half hour before class. So if you were looking like earlier today and you're like, no, it still says it. If you look at it now, it should say that it's actually due next Wednesday. And that's also not a typo, that those next set are due Wednesday, because next Monday is actually the Veterans Day holiday. And so we won't have class. And so I'm not going to make you turn in homework on a day we don't have class. So just be aware of that. But I agree, Matt, the vector fields homework, it's not really that bad. It's just new, just different. So, but are there any specific ones you want to look at, or are we good? Wow, this might be a first. I will take it though. All right, so seeing no questions, I'm going to go ahead and hop over to the whiteboard. So I will check in with you guys in just a second. All right, so last time we talked about vector fields, and hopefully you guys are all good with what vector fields are. Again, they're just functions that are taking us from points and giving us vectors. So they're like vector valued functions, they're just bumped up a dimension or two. And they're used a lot in physics. So for you physics engineering types, you will see vector fields a lot. If you go into atmospheric science, oceanography, you'll see tons of them. So we got vector fields. So let me just remind you how those things work real quick. So they are just like, I'll just do a 2D one. So they're functions f of x, y that give us vectors. And I'll just call the components here g and h. But we do just have two functions of x and y, so two multivariable functions that give us the components of the vectors. So last time we looked at how to draw them, right? Like the domain is easy. It's you check the domains of the two components. We looked at graphing them. Now graphing them is a little bit more challenging than graphing vector valued functions, because now we actually have to have a different arrow for every point that we're in. But I did show you an online vector value or a online vector field grapher. Hopefully you've gotten around and kind of played with those sort of things a little bit, but you'll see they're not that difficult. And then once you see them, you can actually visualize what happens. You can think that if this was, say, a fluid and we were to drop something in there, the particle is going to move in the direction of those arrows. Or if it's a magnetic field and we put something magnetic in it, it's going to move in the direction of those arrows. Or if it's an electric field and it's something charged, it moves in the direction of the arrow. Right? Whatever it is, those arrows are really telling us how stuff is going to be moving. You'll hear me say the flow, how things are flowing, because again, with my background in marine science, I always think water. I always think of these things as fields that are showing motion in water. So you'll hear me say that even if it's not technically what's going on, just realize that's, old man who is stuck in his ways from 30 years ago. 25. Anyway, All right, so vector fields look like this. And then we also talked about a specific type that we call conservative vector fields. These are also sometimes called gradient vector fields. So I'm going to put here, AKA, also known as gradient vector fields. And they get this name because they are such that there is some function such that the field is actually the gradient of f, meaning its components are the partial derivatives of this function. If it's 3D, it'd be fx, fy, fz, right? But anyway, so these are special. This function f, do you guys remember what we call that? The name for that function?
Big F or little f?
The potential
Little
function.
f. Yeah, that's the potential function, right? And so the goal often with potential or with conservative vector fields is finding the potential function. You'll see why, like you'll really see why when we get to the next section, when we get to 6.3, I think it is. That's where you're going to see what why we care about conservative vector fields. They make a lot of integrals a lot easier. But this guy's called the potential function. So we just find that by doing partial integrals, right? You do the partial integral with respect to x on the first piece, partial integral with respect to y on the second one, and then kind of just stick them together, right? Knowing that the constant functions in those partial integrals could be functions of the other variable, but they will be found when you do the other integral. And there's also a good test for these, right? We call it the cross partials test. But you can test to see if it's conservative. For the 2D case, if we call these, shoot, now I forget. Did they use PQR? I think they used PQR.
You used PQR last time.
It's going to be conservative if PY is equal to QX. And so that's the 2D check. 2D check is super, super nice. All right, so it's conservative if and only if PY is equal to QX. If it's the 3D version, so if this is PQR, then there are 3 conditions that we have to check. The first one is PY equaling QX again. But then there's going to be PZ is equal to RX and QZ is equal to RY. So there are 3 we got to check there. It's not terrible, but it's definitely not as fast as the 2D version. Okay, so that's where we got last time, just with the introduction to vector fields. All right, so we get at this point, any questions or we got thumbs up? All right, so I see 1 thumbs up. Thanks, Victor. Appreciate it. At least somebody's paying attention today. Man, my class earlier this morning was horrible. Like nobody was talking, nobody was interacting. So I spent an entire hour and a half talking to my phone. And it's not very exciting. So all right, now
Day, I don't know.
I'm telling you, we're all worn down. You know what it was? You know what it is? It's the stupid time change. Like now you guys know I've got some battles that I fight. Like I'm all about radians. I'm all about metric. Well, I'm also all about let's get rid of time changes. Come on, people. Like they had their day. We don't need them anymore. But
What's up with that, Bruce? Like, why do we actually still have them?
do you want my real answer? What I think
do.
really?
I do.
And this should have been an off the record thing because whatever, but that's all right. I opened the jar, right? The reason, Merca, because we do things the right way. How we've done things are the way they should be done. We don't change. It's the same reason we're not metric. It's like, no, it's the way we always do it. Like our country is super slow to change. If you haven't figured this out yet, just you'll catch on. Give yourself a few more years. But we're pretty bad about that. So, what's up, Jordan?
Also, funny story. They did try to bring metric over here, but the ship carrying all the standardized weights on its way here sank. All the people were like, "Hey, you guys should use this new system of measurement we've invented."
Yeah, that also,
guys got any proof that got any weights we can use to make sure everything's fair? No, they all fell off the ship.
they're in the bottom of the ocean, but don't worry about it.
Yeah.
Nice. That is a fun fact. I had not heard about that, but yeah, I still think the reason that today still we're not a part of those things is because we're Americans.
America.
Yep, America. I digress. All right. So where we're going to go today is I want to introduce you to what we call line integrals. So this is a new kind of integral. When I say it's a new kind of integral, it's still an integral. It's still going to add stuff up, just like any other integral ever did, right? Think about a double integral. We're adding stuff up over a two-dimensional region. Triple integral, we're adding stuff up over a three-dimensional solid. A regular roll integral, we're integrating over an interval, right? It's always adding stuff up. But a line integral, now what we're going to do is it's just a single integral. Yay. We're back to single integrals, and we're going to be integrating some function. And I'm going to go ahead and make this 2D, although 3D doesn't change anything, right? But we're integrating a function, but our differential is going to be ds. So do you remember what ds was? Because we saw that back in like
it's
September. It's not surface area.
It's displacement.
It's not displacement.
Arc length.
There you go. It's arc length.
Yeah.
So
you expect us to remember things from September.
I know, right? What a jerk. Okay, so this is our arc length parameter. Okay, so what we're going to be doing is we're going to be integrating with respect to arc length. So that means that our bounds, if I do this generically, my bounds, I'm going to call it C. And C is going to be some curve. So we're going to be integrating this function along the curve. So since I've got 2D, I can go ahead and draw one here, but let's just say that here is some numeric function of xy. And what we're going to do instead of, like when you think of regular old integrals, you think about integrating from, say, a to b, right? Where a to b are on the x-axis. Now what we're going to do, we're not going to think about it that way. We're going to be integrating from some point on this curve to some other point on this curve. Okay, so this would be C. Now, when you want to think about what is it we're actually adding up, okay? Because like when we did this with single integrals, we saw, oh, we're getting an area, or double integrals, we're finding a volume, and yada, yada, yada. Okay, with this, what we're doing is we're basically dividing this length into a bunch of tiny pieces. We're calculating the distance between all those points, and then we're adding them up. But then we're making it so that we have lots more of those points, so that the gap between any 2 points gets infinitesimally small. So what are we actually getting if we just were to integrate with ds? What quantity?
The length of the
A
curve.
length, yeah.
It's the length. So what this would do, if f of xy was just equal to 1, so if we just integrated ds, this gives us the length of the curve. Just like with a double integral, if you integrated 1, you got area. Triple integral, you got volume. Line integral, you get length of the curve. That's what this is doing. That's how what this is designed to do. So if this function isn't 1, if it's some other function, well, we're still going to be adding up those function values over the entirety of this curve. So I think you can probably already start seeing things that we could use this for. For example, what if you wanted to know the mass of a wire? Well, if you know the density of the wire, if you have a density function, and you were to integrate over the line, you would get total mass over there. So it's whenever you want to add up the total amount of anything along that line. Here's another good example. What if we had a surface? Okay, so we got a surface in space, choose your favorite, right? Elliptic paraboloid or whatever. And you were to draw a curve on the XY plane. If you integrated that surface function over that, what you're getting is actually the surface area of the slice. Right? We've got this three-dimensional solid. We slice through it. So we got a really, really thin little slice. If you want to know its surface area, you integrate that function over the curve, right? Because you're adding up the height on all the different places on the curve, and that gives you surface area. So this is what line integrals are for. Therefore, when you're curious about adding up a function along a path, okay? So it's just giving us a new thing to integrate over, right? Double integrals, we are integrating over a region. Line integrals, we're integrating over a path. Triple integrals, integrating over a three-dimensional solid. Line integrals over a path, can be three-dimensional, it doesn't matter.
So what are some examples of this line integral? Like, would it be like the curve representing the force on an object at any given point?
No, it tends to actually be an actual path, or a curve that describes an actual thing, not necessarily the force acting on it. Because like the force acting on it, that's going to come from the vector field, right? Like the vector fields are what are giving us the forces that would be acting on it. But the line integral, the path would actually be the path that's traveling. So, and we'll get to an example like you're talking, well, I kind of think that you're talking about, Bradley, or I can form from this is, like, think about, we've got an electric field, and we've got a charged particle that's moving here. Maybe we want to know what is the total force, or the total work done by the force on that particle or something like that.
Yeah, something like that.
So you can use line integrals to do that, for sure. What you end up integrating, we'll have to talk about how you form what you're integrating to do that. But that would definitely be an example of where you use line integrals, because we're curious, what is the total work? Let's just go to a work example. What's the total work done on an electron as it goes through a electric field? Well, we need to know the work at this point and at that point and at that point, like what is the work done on all the little different length chunks? Seeing work is force dotted with displacement, right? But then we want to add them all up. And then we want to make them small. And then, oh, guess what? That's an integral. And it's going to be a line integral because we're going over a specific path. So yeah, that's another example of where you could use this. Anytime you wanted to look at how is something being affected along a path by a field, you could definitely do that. For, I think you guys maybe have talked about flux
Yes.
Yeah.
in physics. Yep.
Mhm.
Okay, so if you wanted to look at flux over a path, you could do that as well, right? Where maybe you're not looking at the work done, but if this is some sort of curve, how much flux is going through it from our magnetic field or whatever. Okay,
So
we could
like
calculate-
a wire in a magnetic field and like an electric field, and then you could use this
Sure.
principle.
what's the total flux over that wire? Definitely going to use a line integral.
All right.
So I think you guys are starting to see why mathematicians cared about line integral. Well, maybe more to the point, why scientists wanted line integrals. So mathematicians obliged and created line integrals, right? So there's a reason for line integrals. There are lots of reasons, but this is basically the structure. We're going to have whatever our function is, but we're going to integrate over arc length. Okay, so easy enough, right? Well, easy enough concept, easy enough idea, but think about what this would entail if we really wanted to do it. Like here's an example. Let's do a specific example. Let's say that the density of a wire is given by rho equals x squared plus y. Okay, so just good old x squared plus y. So how much does a wire that follows y equals x squared from the point 0, 0 to 416 weigh? Or yeah, I don't like weigh. That's the wrong word. What mass? How about what mass? Does a wire that follows y equals x squared from 0, 0 to 416 have? Okay, so how massive is that wire?
What fluid is it in?
It's not.
It's just there.
We're not gonna worry about buoyancy or anything like that.
All right. Sorry.
No, that's okay. It's actually a good thing to think. Like as soon as you start thinking about densities and stuff, and but you got to imagine, like if I had like a copper wire, its mass is its mass is its mass. That's why I changed it to that instead of weight. Because weight, then we would have to worry about other forces acting on it other than gravity, and I don't want to do that. Okay, so this is exactly the kind of thing that leads itself to line integrals. I'm adding up densities, so I'm adding up little mass chunks along a path. All right, so we can even go to this and go, okay, well, that's easy. We just got to integrate f of x, y, and then multiply by ds. Okay.
What we need an S.
Okay, so we definitely, well, we need a few things, right? So one, we need the curve. But we know the curve. It's y equals x squared. And we even know from where to where. From 0, 0 to 416. So we know exactly the curve. Cool. We do need an f. Well, what do you think we'd be integrating in this case? Okay, so Victor just put in 1. 1, what that's going to give us is actually the length, If we just integrate 1, it gives us length. So that would give us the length of this wire, which isn't necessarily going to give us the mass of the wire, right? Like I could just tell you, hey, I've got a copper wire that's 10 centimeters long.
We integrate the density function, right?
So it does, we do need to know the density. So in this case, the density is going to be our F. So this guy's our F. This was our C. So, I mean, we've got everything, but it's still not obvious how to set this up. I want to jump back real quick because Victor put something in the chat about going to need to know curvature. Turns out we don't need curvature here. Curvature won't be useful, but we are going to have to remember some things. And I think probably why you went to curvature was remembering arc length had something to do with curvature. I'm just going out on a limb. Yeah, okay. But it turns out that we still kind of have to remember this arc length parameter stuff in order to set up this integral. So let's just at least start trying to set this thing up. I'm not going to worry about bounds just yet. So we're still going to have an integral over the curve, however we're going to define that curve. But the function we are integrating is x squared plus y ds. Okay, so think about the integral in this form. That should immediately be yelling at you. What do you need to do with something that looks like this?
Yeah, convert it and find a Jacobian.
Okay, we're going to definitely have to do some sort of conversion because x's and y's, s, they're not the same.
Plug
Right?
in X and plug in Y.
Okay,
Oh,
so
no. That's not it.
well, but I mean, we could like maybe not plug in x and y, but we do know how y and x are related on this path, right? We're given that y equals x squared, so I guess we could put in x squared here, and so we have an integral of x to the 4th. I mean, does that
Just
make
be
you a little
2x
bit
squared.
faster? Or yeah, 2x squared, whatever.
Sorry.
Shut up, man. Oh yeah, okay, so 2x squared. Like we could do that for sure, since we know the path is y equals x squared. Okay, so just so everybody knows what I'm doing there, I just plug that in there. Does that make you feel better?
No, because I know S is equal to R theta, and I have an X squared and a Y. I mean, why don't we go something like that?
Okay, so we still kind of have that same issue of x and s are not exactly related. Okay, so that's what I was saying. Like in terms of the theory, the idea, yeah, super easy. There you go. I wrote the integral. But that doesn't actually help when it comes to actually doing it. So here's what we're going to do. Here's one of the easier ways of dealing with this is we're going to go back to what we did when we had arc length back in the day. You may recall that there was a way that we related when arc length came up before, it was with parametric equations. That's when we were dealing with arc length. Because before, when we had some sort of a x equals f of t and y equals g of t, we used the arc length parameter so that we could instead write these in terms of s. Right? So you knew where you were not after a certain amount of time, but where you were after you'd traveled a certain distance. So when we were in this world, does anybody remember how we set up the ds, the relationship between ds and dt? Or I'll just even just take s. Okay, so good. So Victor just put in that s was the square root of, what's that? Of v, so r prime. Yeah, so what we know in terms of this arc length parameter, this little ds, it was equal to the square root of f prime squared plus g prime squared times dt. Also known as the magnitude of r prime dt, which I think is what Victor was getting at when he said the square root of a velocity. Okay, so
And
this was
R-
something we talked about this in September, maybe October, early. Again, was like 2 years ago, right? So I don't expect that you necessarily remember where this came from, but at least hopefully you all remember at least seeing it.
Yes.
Is that accurate?
and R
Yeah.
prime of t was the derivative of the position vector valued function, right?
Correct. So r of t would have been f comma g, right? The components, the parametric equations, they gave us the x and the y. Okay. But now this may be enough to help us. Because think about what we had set up here. This whole integral of x squared plus y ds, right? So now instead of just having f of xy ds, we can think of this as f of xy times the magnitude of r prime times ds or times dt. Now we still have the same issue. We have dt's. Here we don't have t's. But maybe because of our experience with parametrics, you see what to do next. What can we do to turn this into an integral we know how to handle? Okay, so Victor just said let f of xy equal r of t. We don't want to do that because r of t, remember that describes the path. F is what we're integrating over the path. So we don't want to do that. But I think you're thinking the
Can
right
we
way.
eliminate the parameter? That was something that we did with parametric functions, right? Or
Yeah, the eliminate the parameter. We kind of want to go the other direction. We want to introduce the parameter. So here's what we're actually going to do. We're going to take this curve and we're going to parameterize it. So instead of writing it as y equals x squared, we want to write it in a parametric form. Okay, so more quiz for class. Do you remember how to do that? Because the actual answer is there's more than one way to do it.
you can set x equal to t and then plug it into the function for y.
But the easiest way would be just to let x equal t and then y equals whatever. So in this case, it's going to be t squared. So if we parameterize the curve, then whatever those components are, we can use those to figure out this magnitude of r, and we can replace our function with those. And so this ends up being an integral that's just going to be in t. So I write here x of t, comma, y of t times the magnitude of r prime dt. Okay, so it's a lot of work to turn it from something that makes total sense. Yeah, we're just integrating over a path. But to get it into a form that we know how to deal with required a little bit more work. So this is probably the one that's down here on the bottom. You probably want to put a box around that, because this is going to be the most useful form of the line integral. So if I just tell you, hey, let's integrate this function over a path, you want to turn it into this. So you want to parameterize the path, use those parameters to create this square root of r prime business, and then your dt. Before we actually bang it out for this problem, I want to bring up something that I think a couple of you guys mentioned. You said something about, oh, we need to find a Jacobian. I love the fact that you went there. And this is actually a great example of where we used Jacobians before, you just didn't know it. When we did this conversion from ds to dt, we always introduced this piece right here, magnitude r prime. That's your Jacobian. That's a Jacobian for that transformation. I never once said it. I never once even hinted that we were doing any kind of change of variables, whatever. But now that you've seen Jacobians, you can see, like, you can spot them now. You can actually go back and look at all the stuff that you ever did. When you did U substitution, every time you did U substitution and you change that dx to something times du, that was a Jacobian.
So basically, anytime we were taking an integral and we had no idea what we were multiplying by something or another was a Jacobian.
Most likely, yeah. Although, don't say you had no idea, right? There was a reason. Like this one came.
Yeah, there was a reason, but like we didn't. It wasn't as easy for us to understand why it was there.
Right. You didn't fully see it, or you just went, okay, well, I mean, I guess I'm multiplying by the square root business because I got to. But yeah, it all falls under that's the Jacobian for doing that transformation from, instead of looking at it as how long we've been going to how far we've gone, that is a mindset. It's changing. It's basically like taking that curve and straightening it out. That transformation requires this Jacobian. So
Crazy.
fun fact, right? And this gets at, and I don't know if this was something that just Bradley and I were talking about during an office hour, or it was kind of at the end of class or something, but I remember not too long ago, we had that kind of discussion and you were like, and this is the same stuff as before. And I was like, oh yeah, like the more you go in math, the more you start recognizing all these things that came before as this later topic. And Jacobians is one of them. Like once you learn about Jacobians, you can start recognizing that you've been doing them ever since we taught you integration. So we just never call, anytime you did any kind of change of variable, pick your favorite time, Jacobians came up. So, anyway, so let's do this one now. Let's actually calculate the mass of this wire, because now we can set this thing up. So we'll go ahead and use this parameterization, t and t squared. So r is going to be t squared. So r prime is 1, 2t. So the magnitude of r prime is the square root of 1 plus 4t squared. So we now have our integral x squared y. If I change those things, it's going to be t squared plus t squared times the square root of 1 plus 4t squared dt. And the last thing I need are bounds. But these need to be t bounds. So what t bounds are we going to use for this path?
So 0 still is one of them. And
I like 0.
4, 0 and 4.
I like
yeah,
0 and 4.
Yeah.
Because if t is just x is t, t is x, I just go to the x coordinates. And we have 0, 4. So is the integral from 0 to 4 of 2t squared square root of 1 plus 4t squared dt. And this equals whatever, I don't really care. Punch it in your TI-89, let it spit it out. If you really want to do it by hand, okay, go right ahead. You can actually get away with this with a U substitution. Even though that's not just t, you can probably still get away with the U substitution. If not, use trig sub, put it in your TI-89. All right, so here's the process. But what's kind of nice is that it doesn't actually matter how you parameterize the curve. We could have done this any way we wanted. So instead of x being t, we could have let x equal t squared, let's say. So then y would have equaled t to the 4th. We would have gotten a different r prime, different Jacobian, because now we're doing a different transformation. The function itself wouldn't look like 2t squared anymore. It would look like, I think, 2t to the 4th or something like that. We'd have different bounds. Like if we'd gone x equals t squared, we would have gone from 0 to 2, because t squared equals 4, right? But if we had set it up properly with a different parameterization, we still would have gotten the exact same value. So that's kind of nice. You don't actually have to worry about, am I choosing the right parameterization? Because it doesn't matter. As long as you have a parameterization that's actually giving you that curve, you're good to go. And when I say you gotta have one that gives you the curve, an example of one that wouldn't, like what if we had said x equals sine of t? Just because we felt like, oh, let's do some trig. Said no one other than me, right? But maybe you got, hey, let's do some trig. Why would x equals sine of t be a problem in this case? Do you see why that'd be an issue?
Because you can't combine the t squared with the sine t.
No, it's not that, because we could
No.
we can do that. We can make y equal sine squared t. That's all right.
Yeah.
How about
Yeah.
this? Oh, go ahead. Who is that? Jacob, go for it.
It wouldn't be as easy to find the r prime, the magnitude of r prime.
That is definitely going to be true. However, that doesn't mean we can't do it. I'm telling you that x equals sine of t cannot work here. Not because it's too hard or anything. But yeah, Victor, it's because of the bounds. Think about sine of t. What kind of numbers come out of sine of t?
-1 to 1.
Between -1 and 1. So we'd only be able to get x's that are between -1 and 1. This has got to go all the way out to 4. So you just have to be careful that not all parameterizations will work, not because of the integral. Like, yeah, the integral could get really complicated if you make this parameterization nasty. But I'm a mathematician. I don't care about difficult or not. I care about, can I do it or not? And there are some parameterizations where it just will not work. So like if I still wanted to go with sine because I was in the mood, I could do x equals 4 sine of t. And that would be okay because that's going to go all the way from -4 to +4, which does cover this x range. Obviously, I wouldn't use all angles. I just have to pick up angles that get me from 0 to 4 once. But so I could do that. I could do y equals 4 sine of t. But in general, just go x equals t. X equals t.
So
Pretty
I'm
much
still,
the only time you're not going to do that is when you already have a specific curve that you're interested in and it's probably already parameterized. Like, let's say we were doing a helix and you wanted to find, you know, the mass of a wire that's in the shape of a helix, so like a spring. Well, we already know a good parameterization for helix, cosine t sine t t. right? So we would just go with that. Hopefully you're seeing what I'm saying. And somebody was just saying something. Let me shut up so they can ask it again.
Yeah, so I'm just still a little confused on how we got mass from this integral.
Okay, because we're adding up the density. So think about this as a density. So it's a mass per length, right? This would be a linear density. So if I take linear density and I multiply it by a little arc length, density times length gives me mass.
Okay, see, I wasn't thinking of it as linear density. I was thinking it as mass over volume.
Oh, okay. No, this is definitely linear density.
Okay, that
Since
makes
we're
sense
talking
then.
about the density of a wire. Yeah.
So would it have to be a three-dimensional for that to be mass over volume, our density function anyway?
Well, we wouldn't use it for a line integral.
Uh,
Or
I
no, we wouldn't use a line integral for that kind of problem.
got it.
If it was a density per area, let's say,
Mhm.
what kind of integral would we use to get the mass of whatever shape?
If it was over area, then a double.
Exactly. So
Okay.
you give me an area density. I integrate that over a double integral. That will give me the mass of a region. If you give me a volume density, I integrate that with a triple integral and I get the mass of whatever that volume or whatever that solid is.
That makes sense. Thank
Okay.
you.
So it's all about, like, I think it's probably a good time to kind of answer that question of, we're getting so many integrals. How do we decide which one to use? And it's all going to come down to what is the question we're trying to answer, right? And so in this case, since we're trying to find the mass of a one-dimensional creature, basically, right, a one-dimensional object, we need a single integral of some type. So now that drops us down to two. We're either going to do a line integral or we're going to do a regular old integral. And what tells us here we want to do a line integral is that we've got a path, not just an interval on the real number line. Right. And so this is kind of where you're going to have to start, how you're going to have to start thinking when it comes to integrals. Is you're going to have to start thinking, what are we doing here? What kind of shape are we dealing with? What is it we're trying to add up? Because then that can push you in the right direction of to which type of integral to use. And just so you know, we're not done. There are more integral types I'm going to show you. Anyway, does that make sense a little bit more?
Yes, definitely. Thank you.
All right, you're welcome. All right, so this is the process. I don't really feel like I need to do more examples because I think you all see just like what you do, how it works, right? It's just a matter of putting in the function, creating a parameterization, and then doing your integral. Okay, so there's your line integral. Now there is there are a couple of variations of line integrals, and I want to go ahead and show them to you. The first variation on this is what we call a vector line integral. And a vector line integral is defined in this way. It's still going to be an integral over a curve, right? So we got a path, otherwise it's not a line integral. But what this is going to be is the integral of f dotted with t ds. So you know it's a line integral because of the ds, right? We're going over arc length and the fact that there's a curve given. But for a vector line integral, we're specifying what we're integrating, right? So before we called this, right, f of xy or whatever. Well, this is the function that we're going to integrate. We're going to do f dotted with t. Okay, now, big F. This is your field. Okay, so vector line integrals are done when we have a vector field. Hence, vector line integrals. That's why these things are called vector line integrals. Okay, so then the question is, what is t? Well, you know the answer to that.
Is that our old friend?
The unit tangent vector. Yep. Which hopefully you remember because it wasn't as far ago as remembering the arc length parameter, right? But yeah, that's just the unit tangent vector. So look at what we're doing. We're taking the vector field. We're going to take that vector, we're going to dot it with the unit tangent vector. And we're going to add that up as we go along the curve. So the unit tangent vector, this is the unit tangent vector, I'm going to say to C, to that path, right? Because when we did this before, when we calculated big T, the unit tangent vector, it was always in terms of a vector value function. We knew that it was always tangent to the curve. It was always length 1, always pointed in the direction of travel. Okay, it's the same deal. It's just the curve that it's tangent to and points in the direction of is C. All right, so basically think of it this way. We've got this curve. We're going to break it down into a bunch of different pieces. So there's a unit tangent vector there, and a unit tangent vector there, and a unit tangent vector there, right? So we've got all these unit tangent vectors. This path is in some sort of a vector field. So at every one of those points, there's some sort of an F. So we're going to dot those things together and then add those all up over the course of the path. All right, so it's just a way that we're going to get what we want to integrate. This is going to take our field and we're going to dot it with T. Before we actually do it though, let's talk about why you might want to do this. Does anybody recognize from physics, like first quarter physics, what this is actually calculating if F is a field that gives us forces?
Won't it give us where we're going?
Doesn't give us where we're going. The T kind of gives us the where we're going. How about think about T? T is an approximation for, let's see, hold on, what was that? Resistance. Nope, not resistance. You're making life way too hard. Oh, well, it's kind of related to like resistance drag stuff ish. Okay, let me help you out. You guys are working way too hard on this. So think about the T as an approximation for going from point A to point B on this curve. What's that also known as in physics language? The vector that shows you where you were to where you are now. Okay, so direction, also called a displacement vector. So kind of what we've got going on here is a force being dotted with displacement.
Work.
Does that help you at all? Yeah, and I don't know if you caught earlier, I said you guys were working too hard. All right, yeah, this is work. What this will calculate is one of the biggest uses of this is this calculates work along a path. Think about the tool I just gave you. Because before, when you had to do work, you only knew how to really calculate work at an instant or calculate work done on a nice like linear path. Right? That's all you ever did back in physics classes. Or even in calc, right? Like I think it was maybe calc 2 when you see work somewhere in there, right?
Yeah.
Well, now you can do work on any kind of a curve. We can do work on a 3-dimensional curve. Go back to the helix example. So let's say we got something spinning on a helix and it's, you know, an electrically charged particle moving through an electric field. You can now calculate how much work is done by the field acting on that particle using a line integral. It's a lot of power. I know it probably doesn't feel like it, but it's a lot of power. And in fact, you guys may have already seen these. Have you seen any line integrals?
I'm sure we have because I was writing our lecture notes and it said line integral, but I can't quite remember what it was for. It might have been finding current.
Sometimes you'll see them with a little circle on them.
Oh yeah.
I had an appointment today to talk.
Wait, the circle?
To go over.
Yeah.
with
Like
him
on the
some,
integral?
you know,
Yeah, that was for
stuff
Flux.
With Ron Yates.
Yeah. You used them for Flux because that's another line integral I'm going to show you. There's also a Flux line integral. So, but when you have the little circle, you use that for a closed curve, closed loop.
Yeah.
Is usually what they're reserved for. So that would be you're looking at flux over like a loop or something. All right, well, anyway, this is one of the biggest things that this is used for is actually to calculate the work done. So if you've got a field, you can actually figure out how much work is done on a particle traveling through it. So let's do this. Let's do something, we'll do something 2D. Then maybe we'll go to 3D, but let's go easy on ourselves here. To start, at least we'll go easy. Let's say this is our path. So we're just going to follow a unit circle, but let's only do a quarter of it. All right, so we're going to go from there to there. And it's the unit circle. So parameterization for this is going to be cosine sine. Let me give you a field. Let's do y comma x. So all this field does is swap the coordinates. So like at the point 2, 3, the field vector is 3, 2. Right. So we could plot it. We could take it, plot this thing and figure out what that field actually looks like. Let's just leave it as it is. But so here's the question. Let's calculate how much work is done by the field in moving along this path. All right, so basically we just have to get F and T and autumn. Okay, well, F is given. It's not exactly given in a good form just yet, though. It's got Y's and X's. So we probably want to go ahead and convert that using these as our X and Y components. Right? So we can fire those in. But let's go ahead and find big T. So y'all remember how to do that, right? He says, hopefully.
The magnitude, or r prime divided by the magnitude of r prime squared
Yeah.
Without the squared.
without the squared.
It's just r prime divided by the magnitude of r prime. Because r prime points in the direction. And then you divide by the magnitude, shrinks it to length 1. Okay, so we need r prime. Well, let's see. R prime is going to be minus sine comma cosine. So the magnitude of r prime is going to be the square root of sine squared plus cosine squared, which, hey, is just 1. Remember, unit circles are nice. Okay, so for this integral then, we're going to have the integral from, we'll worry about from where to where. F is going to be sine t comma cosine t. T is r prime divided by r prime. So that's just going to be minus sine t comma cosine t. And then we still have our ds. We're going to have to worry about that in a second. But there's our f dotted with t. We can probably also put on t bounds. What are the t bounds for this path?
Zero.
0 and pi divided by 2.
Good, from 0 to pi over 2.
Hey, Bruce.
Yeah,
So is sine t comma cosine t our big F?
yep.
And then our big T, I thought was 1.
Nope, the magnitude of it was 1. Big T is r prime divided by the magnitude of r prime.
Yes. Gotcha.
So that magnitude was just 1, so I didn't have to actually change it.
Yep. All right. Thank you.
You're welcome. All right, so the last thing we have to worry about is the ds. So how do we replace the ds?
I know this isn't going to help us at all, but I do remember that curvature is equal to dt over ds.
You're right, that's not going to help us here.
It's going to be square
Think
root of f prime squared plus g prime squared. And f in this case is cosine t. And g is sine t.
Yep, good. We just did this earlier today, so don't give me any of this. I don't remember it from September nonsense, right? The ds, remember what we did? We had to put the magnitude of r prime times dt. Yeah, maybe so. All right, so if we put that in, let's go ahead and just do this dot product while we're at it. We've got cosine squared minus sine squared from the dot product. And then the ds, this is going to be the square root of sine squared plus cosine squared dt. Right? So ds was equal to the magnitude of r prime times dt. That's this right here. Well, again, square root of sine squared plus cosine squared is the square root of 1, which is 1. So if we wanted to figure out how much work is done by this field, we just have to do this integral. So in reality, doing line integrals, you end up doing just a regular old single variable integral. There's just work done. I promise these are not always intentional. Like
Good
that
one, Bruce.
Done finding work. There's something definitely wrong with my brain, no doubt about it. So, but it does require many steps to get to a point where you can do that integral. You do need to change these things. Sometimes you have to parameterize the path, right? Whatever. But once you get there, now this was last year calculus. This is no big deal, right? But it's getting to that point where we can do it. So I'll leave this for you to put an answer in there for right now. It's put smiley face. But whatever it is whatever it is. Okay, now I told you I was going to start easy because this is actually a really easy path. It's easy for us to parameterize it. And the arc length stuff was all nice, right? We got some magnitudes of 1. But before we make it more complicated, and it's not going to be that much more complicated, all I'm going to do is I'm going to actually start and end at the same points. But this time we're going to just make a beeline. We're just going to go straight. Okay, so that's the next one we're going to do. But before we do that, I want to show you something that I don't know if any of you caught. It has to do with R prime. So remember R prime, its magnitude shows up in the arc length. Where else did it show up in this process?
T.
Calculating
T.
T. Yeah.
It showed up in the T, right? So if you think about a generic, we're integrating over a curve f dotted with T ds. If we were to change this, well, this is going to be R prime over the magnitude of R prime. That was the big T. ds is the magnitude of R prime times dt. Notice that those two magnitudes cancel each other out. So they don't actually matter. We needed it, right? But they end up canceling each other out, so it doesn't actually matter. So another way to think about one of these line vector line integrals or work integrals is it's just f dotted with r prime dt. And I'm going to recommend that you put a box around that one, because this is by far the most functional way to do work integrals. Because it cuts out that middleman. We can find r prime fast. Once we've got that r prime, we can dot it with f and be on our merry way. Okay, so let me show you how that would have played out if instead of following that circular path, we had just followed the linear path instead.
So I did that integral just to see what the answer was.
This one?
And
Okay.
yes, does this seem reasonable? 4.1 times 10 to the negative 14.
That sounds reasonable if we call that 0.
Okay. Yeah.
I think that's probably just your calculator with like a rounding thing.
Maybe, yeah. Because
As
that
soon
is
as you get,
really small.
yeah, if you get scientific notation of something like to the minus 14 or whatever, it probably means 0.
Okay.
We'll go with it.
All right.
We'll go with 0. All right, well, okay, so let's go to the context then of physics. Does that happen where you can go on some kind of long path and actually have 0 work done?
Yeah, it depends on whether or not the particle's moving spontaneously.
well, not even
It
that.
can also be a circular path, right?
Okay, well, for some things, if you come back to where you started with, there's no work done. That's for sure. Like gravity is a great example. If I take this pen, lift it up, and then bring it back to where I started, the amount of work done by gravity is 0. Right? Now, that's a return trip, but here, how about this one? If I went from here to there, how much work was done by gravity?
I don't know. 0.
Also 0.
Should be 0 if it's at the same height where it started as where it ended, right? Now, that doesn't mean that the total amount of work was 0, because there are other things doing work. I'm doing work, the air resistance is doing work, like anything that's applying a force is doing work. But gravity itself does work of 0. So getting a work of 0, don't ever be like, oh, that's a problem, because it's not. There are lots of situations where the total amount of work done is 0, even if it's not a closed path. It happens a lot more on closed paths, but not always. We'll get to that. All right, well, let's try doing it on this linear path instead of the curved path. So we're still going to use the same force. Okay, the field is going to be the same, but now we need a different parameterization for that curve. And yes, it's a line. I'm still calling it a curve. Lines are curves. They're just straight curves. So feel free to say straight curve. Don't say straight line. Straight line's going to make me reach in here and flick you on the head. All lines are straight by definition, right? But a line is a straight curve. Anyway, let's parameterize that. So ideas, thoughts, how we can parameterize that path? Okay, so Victor says, let's do x equals t again. Okay, then what would y equal?
-t?
+1.
I like -t plus 1. How about, let's just get the equation of it. If this is a line that's going from, that's connecting the points 0, 1, and 1, 0, right? It's got a slope of -1. It's got a y-intercept of 1. So this is y equals -x plus 1. So if we want to parameterize like we've done before, where we go x is equal to t, then y is going to equal -t plus 1. And I think that sounds like a perfectly fine parameterization. So let's set up our integrals. So the field now is going to be -t plus 1 comma t, because it was y comma x. I need to dot this with r prime. So r prime in this case is going to be 1, -1. It's the derivative of x, the derivative of y, right there. So there's our f dotted with r prime dt. The last thing we need are the bounds on t. So for this parameterization, what are our bounds on t?
0 to 1.
All right, we like 0 and 1. Well, I mean, x is t, t is x, so we really need to know what x's we're traveling over. And x is 0 and x is 1. The only thing I don't like about that is 0 to 1. I don't like that.
Well, depends on how integration man is then.
It doesn't actually.
No?
Not at all. This has everything to do with how we parameterize it. Think about, where do we start on this path? Which point are we starting at?
I guess 1.
We're starting over here at 1, 0. So that's our initial x is 1. That means our initial t is 1. And then as we move in this direction, our x's are going down to 0. So our t's are going down to 0.
I don't understand how, if this integral is finding the length of that straight curve, how there would be any difference in the order of our bounds.
Okay, because it's not finding the length. This integral is not finding the length. It's actually finding the work done.
Gotcha.
And so the work done absolutely matters where you start and where you end. And Seamus, I don't know you. Have you taken much physics?
I took non-calculus physics.
Okay, but so
But I have an
probably
understanding, yeah.
Yeah, okay. So you'll probably remember then that work, actually, if you go from A to B, you get the opposite of going from B to A. Maybe?
Yeah.
For a lot of fields or forces.
Yeah.
That's what happens, like with gravity. And so order does matter, direction does matter when you calculate these things. If all we were doing was integrating 1, which would give us the length, then no, it doesn't matter. Because if we did 0 to 1, yeah, that's going to give us our length. But that's not the direction we're actually traveling here.
I gotcha.
So something you definitely have to pay attention to, right? And it has to do with these bounds. Watch the direction of travel. Or maybe watch isn't the right word, it's pay attention to. Because you can watch things and not pay attention to them. Think about my lectures, right? All right, so pay attention to the order of travel, because that matters, especially when we're talking work. Okay. Quite often, if you go the opposite direction, you will get a different value. Not always, but sometimes. Usually. All right, so this is what this is going to be. It's going to be an integral from 1 to 0. And I know you really don't like integrating bigger numbers to smaller numbers, but it doesn't matter, right? We still use the fundamental theorem. We still calculate it the same way, no big deal. This one, if we do the dot product, we're going to get minus t plus 1 minus t right? I got that right? I think so. So we're integrating from 1 to 0 minus 2t plus 1 dt. And well, d squared, how about dt? I'm way too lazy to calculate that. Although that's pretty easy. Hold on, I'll just power through it. Minus t squared plus t at 1 and 0. When I plug in 0, I get 0. When I plug in 1, I get minus 1 plus 1, which is, oh, hey, 0. All right, so on that path, we ended up getting 0 as well. Which may now make you start thinking.
I sense it's not a coincidence.
You might start thinking, well, does it matter how we go there? Are we always going to get the same thing? Well, let's try one more. This time, though, let's do this path. Let's go from 1, 0 to 0, 0, and then up to 0, 1. So we're just going to follow the axes. Okay, now this way kind of sucks because we're going to have to do two different line integrals. I think it's pretty clear why, right? We're going to have the one line integral as we're going along the x-axis, and then we're going to have another line integral as we go along the y-axis. However, even though we have to do two of them, they're not terrible, right? I mean, the parameterizations are going to be easy. So let me label them as 1 and 2. So we'll talk about the different paths for 1 and for 2. So for 1, here'd be a good parameterization. Let's again let x equal t, but we're going to let y equal 0. Because on that axis, y is always equal to 0. And for the t's, we're going to go from 1 to 0, just like we did before, right? The x's are going to start at 1 and go to 0. So here's what that integral is going to look like. We're going to integrate from 1 to 0. The function, the field, is going to be 0, t. And we're going to dot that with r prime, which in this case is 1, 0. So when we do that dot product, we get 0 dt. And of course, integrating 0, I don't care how you integrate it, we get 0. So the amount of work that's done as we go from 1, 0 to the origin is 0. Cool. So now let's look at path 2. Because we'll just add these things together once we get the other one. So the second path, how about for that one, we go with 0, t. Because the x coordinate is always 0 on the y-axis. And the y's are changing, right? And this is going to be t going from, in this case, 0 to 1, what you like. Okay, so we're going to integrate from 0 to 1. We have our f. Well, f is going to be t comma 0. Again, it's the y comma x. We're going to multiply that. We're going to dot that with r prime. Well, r prime is 0, 1. Well, that dot product again gives us 0, which means that integral is equal to 0. So here was a third path that also gave us 0. All right, so what are you thinking? Does it matter the path? Are we always going to get the same value?
No, the path doesn't matter.
All right. Well, I will tell you this. In this case, the path does not matter. Which path we choose doesn't matter. We're going to get the same value every time. However, that is not always the case. And the reason that we were able to do it this way was because of f. This field right here is special. Okay, this is a special field that it turns out no matter where you're going, A to B, whatever those points are, it doesn't matter what path you take, right? Like I could have done this path. Here's path number 4. We're not going to try to calculate this one, but path number 4 would be, let's go. Okay, so imagine doing some parameterization for that thing. Turns out the work done, total work done is still 0. But it's only because of this field right here. If this field were different, we would have different results. Let me show you. All right, so let's just change it ever so slightly. Oh, shoot, I don't have time. It's 2:40. So this is gonna be the first thing we do next time, is I'm gonna change this field ever so slightly. Like literally, this is all I'm gonna do. I'm gonna make it y comma negative x. I'm just gonna change the sign on the x. That's it. And we're gonna see that we get very different values.
So it's
All right,
safe
well,
to
anyway.
say that we can't always assume that the path traveled doesn't matter.
No, but I am going to show you how to tell. Because like, I'm not that big of a jerk, you know that, right? I will definitely share with you how you can recognize that like yx is a good field and y negative x is not a good field, at least in terms of the path independence, right? So there is a check. I will share that with you. Do not worry. Have no fear, right? But it's not always the case that path doesn't matter. Okay, so that'll be the very first thing we do on Wednesday. Go ahead, Bradley.
Does it depend on conservative versus non-conservative fields?
Maybe.
Okay, I'll wait.
Dude, I'm not going to show you my cards. If I tell you now, then nobody comes back on Wednesday. So, right? Like they teach you as a teacher. And don't worry, I actually never took an education course in my life. So I've not been trained to be a teacher. I just wing it, you know. But I do know that one of the things they teach you as a teacher is to give the hook, the try to get them back next time. My mentality has always been, dude, if they don't want to come back next time, that's on them. They're just going to miss out on all of this, the fun chaos that is Bruce's math class. Anyway, so the other thing I just want to remind you real quick, don't forget homeworks due tonight. I think they're just the 2 sets since I eliminated the one on centroids and moments of inertia and stuff. But anyway, make sure you get that done by midnight tonight. And other than that, we will call it a day.